So I will start right away from my introductions. So since the first exfoliations of graphene, the science has revealed the numerous characteristics of these exotic two-dimensional materials. With its atomic thickness, it possesses unique characteristics such as electronic and magnetic and mechanical properties. So represented by graphenes and transition metal like cosmos, they exhibit characteristics such as high calorie mobilities and terminal band gaps. It makes them very valuable for advanced applications. So on the other hand, this polar orders and its associated hysteresis behaviors has played crucial roles in modern electronic devices. These ferroelectric materials will feature polarization hysteresis upon switching the external field. It is crucial for high-density data storage and microwave devices and advanced materials. So, taking this ferroelectric field effect transistors for examples, if you can be used to build one transition non-volatile memories. In the FET ferroelectrics, it is employed as a gate insulators, so that the channel conductance is used to detect the polarization state in the gate, so that data readings operation of this FET is non-destructive. So ferroelectric FETs is a promising memory technology due to this fast switching speed of these ferroelectric materials and non-destructive readouts and simple structures for high densities integrations. So with the rapid increasing demands of this data storage, there's no surprise in that research efforts is a strong desire to reduce the dimension of this ferroelectric device with exploring new materials such as 2D semiconductors like this one. So the problem is that in the case of 2H-based TMDs, the preserving of these central symmetries will directly result into these incompatibilities of ferroelectricities. Therefore, development of these devices has just been stolen for past few decades. But luckily, if this horizontal plane of the transition metal layers could be broken, such a case of distorted 1T phase of MOS2, then the slight vertical displacements of interlayers of atoms will result into broken symmetries, and a net electron polarization along the outer plane will emerge. Then the lattice space group may reduce into ferroelectric subgroup. Then the emergence will happen for ferroelectricities. So, and interesting research that has just been published by one of our respective collaborators, Professor Lance. His group provided strong evidence that the shear transistor bilayer MOS2 systems with a broken mirror symmetries between the two MOS2 modules will give rise to ferroelectricity's response. So, very similar research that has also been reported in multiple van der Waals interface between two twisted van der Waals materials without any polarization point group in the pristine lattice by causing just strains and small distortion in two layers, such as boron nitrides and of course TMDs. So with a small lattice distortion between these 2D layers, we believe that it is similar systems is highly possible to host such ferroelectricities, but how did these related to the Moire superlattice? Since my topic today is this evolutions of Moire superlattice. So to resolve this, I want to firstly show the inspiration of the experiments I will later conduct, which is inspired by one of famous collaborator, Professor Ye, in Caltech, US. They have discovered a unique ferroelectric-like hysteresis behaviors under our plane magnetic fields in the field effect transistor based on Moire and MOS2 on silicon oxide substrate. So, as the first figure demonstrates, you can tell that upon applying an outer plane's magnetic field, for example, 9 Tesla here, a counterclockwise hysteresis loop will emerge from the measurements of FET device at about 1.8 kelvins. This hysteresis will open windows will increase as the magnetic field slowly increase and then saturate for larger figures. More, the size of this hysteresis loop will expand as the temperature drops down and also saturates around 14 Kelvin. So, on the other hand, there will be no loops of this hysteresis behavior present at zero field applied or any temperature above 20 Kelvin. So, on our first instincts, we might suggest that it could be a kind of magnetic field-induced phase transistors at the low temperature, since only one T phase of MOS2 could hold such ferroelectric response. So, to elucidate this origin of this stunning phenomenon, we further carried out a Raman spectroscope, and with the help of our collaborator professors Liu in National Taiwan Universities. And upon cooling the sample to about 20 kelvins, both the A1G and E2G peaks were found blue shift due to the positive thermal expansions as we expect. But if we apply an outer plane magnetic field, we could see that a significant redshift will found at about 4.2 kelvins. So these findings strongly suggest that under magnetic field below certain temperatures, MOS2 lattice will experience a tensile strain that gives rise to the small lattice expansions instead of the phase transition that we think before. So now the questions start to pop up, like we can't help but wondering how does these lattice expansions induce the ferroelectric response that we have observed, and how it is possible to probe this difference, and then can we quantize, analyze this change in real space. And that's how the STMs comes in this experiment. So scanning tiny microscope, I believe most of you know this as a STM that we referred, is a very powerful tool that by means of quantitonic effect, if we apply a voltage difference between the metal tip and the conductive samples, electrons will tunnel through the gap in between. And tonic current is very sensitive to the density of state of samples and the very high, which is mainly the distance between the sample and the tip. So if you use piezo feedback systems, we could probe the samples topographies within the tonic resolutions by just keeping the same tonic current. So now we have this tool. But if we analyze this Raman spectroscope, we can find that this redshift under magnetic field applied, the lattice expansions was roughly only 1% at 0.5 magnetic field applied. So in this case, it is extremely difficult to precisely probe these tiny variations in real space, even with our low temperature STM. So therefore, we come up with this idea that instead of probe the MOS2 lattice directly, we choose to use the STM to study the Moire superlattice of MOS2. So for those who were unfamiliar with Moire pattern is a larger superlattice that will appear if we stack two periodic layers on top of each other, just like the animations that I'm showing right now. This superlattice pattern is very common in our daily life and will also be observed in atomic scale. So for any 2D materials, by just giving a lattice mismatch between two stacked layers with different twist angles, it is very simple to determine its Moire superlattice. Where the lambda here is the Moire periodicities, delta is the lattice mismatch between the film and the substrate, and the theta is the relative angles between the film and the Moire, and phi is the twist angle between film and the substrate. So by plotting these theoretical models, we could see that as the MOS2 lattice expands, the Moire periodicities will simultaneously decrease roughly 10 times as fast as the MOS2 expand. So since a slight difference of the lattice on top layer MOS2s will cause a huge difference of Moire, then we could probe this difference and then use these correlations to calculate the small lattice expansion of MOS2. And also, if we look carefully, we could see that as the MOS2 lattice expands, the relative angles theta will start to rotate. This is due to the lattice mismatch that will change in this theta functions that will change this relative angle thetas, so that this rotation in real space will happen as the MOS2 expands. So therefore, in this work, we will study more superlattice of MOS2 on HOPGs at 4.2 Kelvin on the magnetic field applied with our STMs to determine the lattice variations. So here I will first demonstrate the MOS2 on HOPG under 5 Teslas. So after the effective filters, we could obviously see that Moire patterns will appear and remain the same periodics, which is very important within the MOS2 bandgap, and could only observe the Moire signals out of the bandgap. Where the red circle here indicate the Moire signals, and the blue one indicate the MOS2. And in our observations, 0.1 volt, we can get the most clear and sharp lattice signal. So therefore, we choose these values in our further data analyzations. So now we demonstrate the image under different magnetic fields from 0.5 to 3 Tesla to 5. On the different magnetic field applied in real space and reciprocal space, the image that we're showing right here. If we first analyze these topographies and FFTs, we could already calculate the Moires and the MOS2 lattice constants, which feature shrinkings and of Moire and the expansion of MOS2 lattice simultaneously as the magnetic field gradually applied. This is the direct evidence and verify the expansion of MOS2s, and this expansion is strongly dependent as the magnetic field. As you can see, that it's getting bigger as the magnetic field applied, and about 1% to 3% as the field from 0.5 Tesla to 5 Teslas. And as we put in this data back into the theoretical models, as the orange dash line illustrates, we could see it matched pretty well with it, and from 0.5 Tesla to 5 Teslas as the magnetic field applied. And also, we further conduct this experiments on other region on the samples, as the green dash lines illustrate right here, which also shows a measured result as this experiments conducting. And particularly in these regions, we observe a different twist angles between the MOS2 and the substrate. So that's why these different lines isn't overlapping. And in these regions, our main purpose is to verify that in the different regions, the lattice expansion will occur no matter the twist angles or the domain difference. So that's why we could only get the extension data from the Tesla to 5 Teslas. So the overall message that I'm saying right here is that, as the figure demonstrates, this phenomenon is robust and reproducible, and it's the first observation we could spot on date. And also, if you remember that, as we mentioned above, the relative angles between the Moire superlattice and the MOS2 will rotate due to lattice expansions. So using the same models applied, we could also determine their correlations where the relative angle of thetas getting smaller as the MOS2 lattice expands. This trend was also in a good agreement with our measurements. So one thing worth notice is that under different magnetic field applied, the HOPG substrate will remain the same lattice constants. So that's why we could deduce the variation solely came from the MOS2 lattice, since the delta function here is only changing by this lattice constant of the field, which is MOS2. So with our findings in above, we could confirm that in real space, MOS2 lattice will experience and tensile strengths that will give rise to lattice expansions instead of the phase transitions to 1T phase that we thought about. So on top of this evidence, we further deduce this exotic ferroelectric response could result from asymmetry lattice expansions between the top layers of the atoms and those bound with the substrate. So since our MOS2 is on a rigid silicon oxide substrate in this FET device, this expansion coefficient mismatch between the MOS2 and the substrate will lead to a symmetry flexo electrical effect, which could rise to the outer plane polarizations, and therefore to our observation of magnetic field induced ferroelectric-like hysteresis behavior. So one aspect that is worth notice is that we further verified the importance of the substrate in account of symmetry lattice expansions and results polar effects by studying another FET devices with HBM buffer between the modulated MOS2 and this rigid silicon oxide substrate, like this picture is showing right now. So since HBM has a similar expansion coefficients with MOS2, the lattice expansions then become symmetries between the MOS2 interlayers. Thus, the results of these FETs show no hysteresis behavior, just as we expect. So now for the final summarizations. In this work, we have confirmed that MOS2 lattice will experience roughly 1 to 3% of expansions upon outer plane magnetic field applied from 0.5 Tesla to 5 Tesla, which results in an obvious difference in the relative angle phias and the Moire periodicities. This result is also matching with our collaborators' partners' Raman spectrums, and a lattice expansion on the rigid substrates with expansion coefficient mismatch will lead to a symmetry flexo-electric effect, which give rise to these outer plane polarizations, and therefore to our observation of the magnetic field-induced ferroelectric hysteresis behavior. So this work has already been published in just last month. So please check it if you're interested. And before I finish my talk, I also want to introduce the institute that I'm working at. I'm currently a PhD student at National Army University under Professor Lin's lab. Most of you know him as Lin Sons, and our current postdoc is Carl Sons. If you are interested in collaborations with us or simply working with us, please contact my supervisors. And it is all my presentations. I hope you enjoy, and thanks for listening.